Welcome to This Explainer. We're treating today like your very own elite ground school session, preparing you for the cockpit with a super welcoming, no gatekeeping approach. Whether you are an aspiring pilot or just deeply fascinated by aviation, true confidence in the left seat comes from really understanding the machine around you. So we're going to break down the complex systems that keep us safely in the sky. All right, let's take a quick look at today's syllabus. We'll be covering 5 main areas. 1. Brakes and flight controls. 2. Fuel systems and carburetors. 3. The aircraft electrical system. 4. Climate control and warnings. And finally, 5. De-icing and anti-icing. Starting off with Section 1, Brakes and Flight Controls. Let's make our very first stop on this virtual hangar tour and focus on exactly how we stop and steer the aircraft. To really ground our learning, we're going to compare 2 classic study aircraft, the high-wing Cessna 172S and the low-wing Piper Arrow PA-28R201. Now, for both of these birds, your foundational ground control relies on single-disc, independent toe brakes. What's really cool is this hydraulic system is totally separate from the landing gear hydraulics. It's actually fed by its own dedicated reservoir tucked securely away on the left side of the firewall. Moving on to flight controls, the Piper Arrow uses plane flaps that you manually operate from 0 to 40 degrees. Now, extending these fundamentally changes your aerodynamics. It amps up your parasite drag and increases your descent rate without actually increasing your airspeed, all while crucially lowering your stall speed. Pretty handy, right? Now, for yaw control, we've got a conventional rudder. It has a mechanical trim tab that literally repositions your rudder pedals to create a brand new neutral position. This perfectly corrects any tendency for the fuselage to fly out of alignment with the relative wind. This brings us to a really clever piece of engineering on the Arrow, differential ailerons. When you initiate a roll, the aileron deflecting upwards moves 23 degrees, but the one going down only moves 17 degrees. You might be wondering, why the difference? Well, the wing that goes down, the one with the 23-degree aileron, creates extra parasite drag. This is by design. It perfectly matches the induced drag created by the opposite lifting wing, which keeps the nose from yawing in the wrong direction. It's all about perfect aerodynamic balance. For pitch control, the Piper rocks a one-piece stabilator. Because it pivots on a hinge located about 2/3 of the way back, it's incredibly aerodynamically effective. But there's a catch. It has a dangerous tendency to over-control. That's exactly where the anti-servo tab steps in. By moving in the exact same direction as the stabilator, it fights that movement just enough to give you, the pilot, the necessary control feel. Plus, it adds vital tail-down force for longitudinal stability. Literally a lifesaver. Moving right along to Section 2, Fuel Systems and Carburetors. Let's see how our control foundations build into the beating heart of the aircraft, the engine and its fuel source. Okay, so our Piper Arrow holds 77 gallons of 100 or 100 low-laid aviation fuel. But here is an absolutely critical safety fact you need to know. 5 of those gallons are completely unusable. Why on earth would we intentionally leave fuel behind? Well, that bottom layer acts as a trap. It catches dangerous dust, sand, and dirt, completely preventing them from ever reaching the engine. The usable fuel then flows through a selector valve, normally driven by an engine-driven pump. But you also have an electric pump serving as a super vital backup during critical phases like takeoffs and landings. Now, the way the float-type carburetor breathes life into the engine is just fascinating. Filtered air rushes into a narrowing venturi. Think of it exactly like putting your thumb over a running garden hose. The air speeds up, and that creates an area of low pressure. This low pressure literally sucks the fuel right out of the float chamber, mixing it perfectly with the air before sending it into the cylinders to burn. It is wonderfully simple and reliable. But that simplicity does hide a serious danger. Because of that sharp drop in air pressure and the fuel vaporizing, the temperature inside that venturi drops like a rock. In fact, it drops so dramatically that if you're dealing with 80% humidity, dangerous carburetor icing can happen on a surprisingly warm 70-degree Fahrenheit day. No way, right? It's true, and it's especially common during low-power descents when your engine heat is much lower. So that begs the question, how do we prevent this invisible ice from just choking the engine mid-flight? The answer is applying carburetor heat. By actively routing warm air into the carburetor, we fight off that sharp temperature drop inside the venturi. This melts any ice that's already formed and guarantees our fuel-air mixture keeps flowing smoothly. All right, on to Section 3, the aircraft electrical system. Let's transition to the invisible nervous system that powers everything from our avionics to our starter. To wrap your head around this, think of electricity just like water flowing through a pipe. Voltage is your water pressure, and amperage is the actual volume of water flowing. The Cessna uses a 28-volt system. Because it has higher pressure, it needs less volume, meaning fewer amps to do the exact same amount of work. This lets engineers use thinner, much lighter wires. The Piper Arrow, on the flip side, uses a 14-volt system. Sure, the wires have to be thicker and heavier, but the whole setup allows for significantly smaller and, frankly, cheaper battery. So, the crucial thing here is understanding exactly where our power comes from. Once the engine is running, a belt-driven alternator becomes our main power source. Alternators are awesome because they efficiently crank out alternating current, or AC, even when engine RPMs are super low. But there is a catch. Our battery and all those vital cockpit instruments, they run on direct current, or DC. To solve this, the aircraft uses a neat little device called a rectifier to instantly convert that AC power into the usable DC power we need. Now, electricity is volatile, so we have multiple layers of protection built in. For instance, the alternator control unit has a relay that immediately cuts the alternator off if it spikes over 14 volts. We keep an eye on system health using either an ammeter, which tells us if the battery is actively charging or draining, or a load meter, which just shows how hard the alternator is working. If you ever face an electrical overload of more than 20 amps, your absolute first step is to flip that battery switch to off and then immediately run your emergency checklist to prevent a fire. Let's move into the cockpit for Section 4, Climate Control and Warnings. We're going to explore how the pilot stays comfortable and, more importantly, safe from unseen atmospheric threats. Ever wonder how we actually get heat at 10,000 feet? It's pretty clever. Cold, fresh ram air enters the nose of the aircraft. It's then ducted right into a sealed heat shroud that completely wraps around the dangerously hot engine exhaust pipe. The heat simply radiates through the metal, safely warming that fresh air, which is then vented directly into the cabin to keep you warm and up to the windshield for defrosting. But listen closely, because this brilliant design comes with a potentially lethal caveat. If that exhaust pipe ever develops even a microscopic crack, toxic, completely scentless carbon monoxide gas will mix directly with your cabin air. This is a massive, incredibly serious emergency. If you ever, under any circumstance, smell exhaust gas while that heater is on, you need to turn the heater off immediately and pop open all your fresh air vents. I don't care how freezing cold it is outside, you do it immediately. Switching gears to another absolutely critical warning system, the stall detector. You'll find this located right on the leading edge of the left wing. It's specifically designed to alert you 5 to 10 knots before you ever hit that critical angle of attack. It's actually really interesting to look at the design differences here. The Cessna uses a pneumatic system that literally relies on the suction of the outside air to physically blow a horn. Meanwhile, the Piper Arrow goes a different route and utilizes a purely electronic stall warning horn. And here we are at Section 5, de-icing and anti-icing. Let's cover structural ice defense mechanisms, breaking them down into de-icing, which removes formed ice, versus anti-icing, which prevents it from forming at all. All right, let's talk ice defense. Now, massive commercial jets can just use scorching hot bleed air straight from their turbines to melt ice away, but our prop planes require some totally different solutions. First, anti-icing. Some aircraft use what we call weeping wings. These are laser-drilled microscopic holes on the leading edge that actively pump out a glycol and alcohol mix to keep ice from ever sticking. Then we have de-icing. For this, we use pneumatic boots. They're basically thick rubber sheets on the leading edge that sequentially inflate with air to physically crack and break off any formed ice. Of course, keeping our forward vision clear is absolutely paramount. Windshields can be protected by standard heated air defrost, a dedicated flow of alcohol, or even cyclic electric heat panels that are actually embedded right in the glass. And the propellers? They have their own ingenious line of defense. Alcohol is discharged from nozzles right at the spinner. Then the sheer centrifugal force of the spinning blade drives that fluid perfectly down the leading edge, stopping ice completely dead in its tracks. Well, we've covered the whole shebang today, from differential drag all the way to the chemical energy of your battery. A pilot's true power doesn't just come from having great hands-on stick and rudder skills. It comes from a deep, absolutely uncompromising understanding of the magnificent machine around them. This technical mastery is the literal foundation of safe, confident, and professional flying. So the question is, after mastering all these complex systems, are you ready for the left seat?